Okay, this is section 2.6. So we've gone through a bunch of the differentiation or derivative rules. We've gone through the power rule, the product rule, the quotient rule, the trig derivatives, and the chain rule. Now we're going to talk about something which is called implicit differentiation. Technically, we've been doing implicit differentiation. We just didn't realize it. And I'm going to kind of try and explain that a little bit, but then I'm also going to try and simplify it so that we don't always have to think about everything that we were doing as being an implicit derivative. It has been, but probably better off to just go ahead and think of everything that we've been doing the way it is. Again, I'll explain all that when we get to it. So far, the functions that we've had have been expressed in what's called explicit form. Meaning, like y equals 2x plus 3, the variable y is explicitly written as a function of x. Basically, we can solve that for y as a function of x. Some functions are only implied by an equation. An example of that might be xy equals 1. So if we wanted to differentiate xy equals 1, well, we could actually do that by solving this one for y. So we're going to go ahead and solve the equation for y by dividing both sides by x. Okay, and then we can change 1 over x to x to the negative 1 power. Now we can use the quotient, the power rule. So if I want to take the derivative of y, I'm going to write it as dy over dx because we are taking the derivative of y with respect to x. And then that's going to equal the derivative of x to the negative 1, bring the negative 1 out front, reduce the power by 1. So really what you get is negative x to the negative 2, which is the same as negative 1 over x squared. Okay, that's not too bad, and that one actually works quite well, that strategy, if we can solve the function explicitly. So the problem is you cannot use that procedure when you're unable to solve for y as a function of x. So an example of that would be x squared minus 2y cubed plus 4y equals 2. That expression right there would be very, very difficult to solve for y as a function of x explicitly. So what we can do is we can use this thing which is called implicit differentiation. And implicit in this case means that we are implying something. Okay, something here is going to be implied. All right, so let's actually take a look at the next page here. There we go. And see if we can't figure this out. So to understand how to find dy over dx implicitly, you first have to realize the differentiation or the derivative is taking place with respect to x. And basically what that means is x is your independent variable. Okay, it's the thing where it would be your input. You would input something into x, and then you would get out something for y. That means that when you take a derivative or differentiate terms involving x alone, you can differentiate or take a derivative like we've been doing. But when you differentiate terms involving y, you have to apply the chain rule because y itself is a function of x. It's defined to be a function of x. So what do I mean exactly by that? Well, we should know that for the most part, we can almost interchange y and f of x. They kind of mean the same thing as long as it's an actual function. So if I was to take the derivative, or let's just say that y equals x squared, and we were to take the derivative of that. Now, when you take a derivative, you take the derivative, just like anything else in algebra, of both sides of the equal sign. So the derivative of y, we could write y prime, but in this case, I prefer the dy over dx symbol. And then the derivative of the right side of the equation is 2x. Okay, that's not really that challenging to do. But what happens in a case where we can't necessarily separate that and solve it for y explicitly? Well, let's take a look. What we have to think about here is that we've got y cubed plus y squared minus 5y minus x squared equals -4. We're going to take the derivative of both sides of the equal sign. The y cubed part technically is y in parentheses cubed, because y itself is a function of x. Okay, now this is where it gets a little bit challenging. I would have to apply the chain rule to that. So when I take the derivative, I'm going to bring the 3 out to the front and reduce the power by 1. But then because y is a function of x, I now have to multiply it by the derivative of y, and the derivative of y is dy over dx, just like right there. Okay, the same exact thing is going to apply to the y squared. Again, imagine that there's a parentheses around the y. So I would bring the 2 out to the front, reduce the power by 1. Now I'm not going to actually write the 1 up there because it looks like a prime symbol. This is why I don't use the y prime. And then I have to multiply it by the derivative of y, which is dy over dx. Okay, and the next piece, 5y. Again, imagine that the y is in parentheses, so it would be 5. You would bring the 1 out to the front and multiply it by the 5. You would technically then have y to the 0 power, so really that goes away, times the derivative of y, which is dy over dx, minus. I'm going to do exactly the same thing as I've been doing with the y's. I'm going to do it with the x's. So again, imagine there's a parentheses around the x. I would bring the 2 out to the front, reduce the power by 1. Then technically I would have to multiply that by the derivative of x, which is going to be, if you put it into the notation that I've been using, it's the derivative of x with respect to x. But of course, dx over dx is 1. So really that kind of just is 1. It goes away. And then the right side derivative is the derivative of -4, which is 0. So just kind of cleaning this up, we would get 3y squared dy over dx plus 2y dy over dx minus 5 dy over dx minus 2x equals 0. That would be the derivative of that expression. Now, let's simplify this a little bit, because everything that I just told you there sounded a bit confusing. The easiest thing to think of is if it's just got x's in it, or if it's just got your independent variable in it. And by the way, you can always tell what the independent variable is in the derivative. It's the one on the bottom. If it's just got that variable in it, you're just going to take the derivative like normal. And that's kind of what happened here. We ended up just getting a minus 2x when we took the derivative of minus x squared. Everything else, when it has like the y's in it or whatever your dependent variable is going to get multiplied by dy over dx, or d whatever over the independent variable's derivative. So it's going to look like a dy dx. So most simple form, if you've got y's and x's and you take the derivative with respect to x, if it has a y in it and you take the derivative, you have to multiply it by dy dx. If it doesn't have a y in it and it's just got an x in it, you take the derivative like normal. All right, one more thing I want to show on this specific problem is I actually want to solve this for dy dx, because that's kind of what it's asking us to do here. Solve for dy dx. In order to solve this expression, the derivative here for dy dx, I'm going to have to isolate all the terms with dy dx on one side. Well, I've got 3 of them over here. Only that minus 2x doesn't have one. So I'm going to add that 2x to the right side and keep everything else on the left. So add the 2x to the right. Now I've isolated all the terms with dy dx, so I can factor the dy dx out. And that's going to leave 3y squared plus 2y minus 5 equals 2x. And then I'm going to solve for dy over dx by dividing by the entire parentheses. So we get that our derivative with respect to x is 2x over 3y squared plus 2y minus 5. And one thing I really want to point out here, this derivative is different than every other derivative we've done so far. And if you've kind of been looking at it, you might think, well, wait a minute, there is something different about it. This derivative has y's in it, not just x's. What that tells me is that the slope of this expression right here, that equation, is not only dependent upon x, it is also dependent upon the y value. Okay, and we'll actually look at an example, hopefully that will make that make sense. A lot of times when you have things like this, the original equation may not be a function. It's an equation, but it's not necessarily a function. All right, let's go ahead and move to the next page. So guidelines for taking implicit differentiation. Differentiate both sides of the equation with respect to x. Collect all the terms involving dy dx on the left, and then move everything else to the right. That's interchangeable. If you've got more terms with dy dx on the right, move them all to that side, as long as you get them to one side or the other. Factor out the dy dx, and then solve for dy dx by dividing both sides by whatever's left over in parentheses. All right, let's try a couple of examples. X squared plus y squared equals 16. So when I take the derivative of x squared, we do that just like it was anything else. The derivative of x squared is 2x. The derivative of y squared now is where you have to apply the chain rule. It'll be 2y, regular derivative, times the derivative of y, which is dy over dx. And then the derivative of the right side is 0. So now we have to solve that expression right there for dy over dx. So we can subtract 2x on both sides. And then we can divide both sides by 2y. And we get that dy dx is negative 2x over 2y. Of course, the 2's will cancel out there, so we get negative x over y. And again, what that means is it means that the slope is dependent upon both x and y. So if you happen to know what this expression is, okay, this is the equation of a circle with a radius 4 centered at the origin. Something like that. Negative 4 here, and so on. The idea behind what I was trying to get across here is, normally, if I was to say, okay, what's the slope when x is 2? If I go out to x is 2, and go up here, the slope of this thing is going to be whatever the slope of that tangent line is right there. However, there's another place on this circle when x is 2. It could also be down here, which means that the slope is going to be different at that, at that particular spot. So it is not only dependent upon the x value, but it's dependent upon the y value as well. And you're going to have multiple slopes. And as you can see, a circle is not a function. So what we started off with originally was not a function, which is why it has potentially multiple values of slope for given x and y values. Again, so hopefully that makes some kind of sense. The derivative or the slope of that circle is dependent upon both the x and the y value. All right, let's do another example, number 2. All right, so number 2 is x squared y plus y squared x equals negative 2. What you should see is this part right here is a product. This part right here is a product. We are going to have to do 2 product rules in order to find this derivative. So let's go ahead and take the derivative. In this case, in the first part, got 2 functions, x squared and y. So the derivative of the first one is 2x times the second one, y, plus the derivative of the second. The derivative of y is dy over dx times the first one, x squared. That took care of that first term, x squared y. Okay, that's all the first term. Plus, now I have to do the derivative of y squared x. Again, product rule, derivative of the first, 2y dy over dx times the second, x, plus the derivative of x, which is 1, times the first, y squared. That's the second one. And then equals 0, because the derivative of -2 is 0. So notice, and this is going to be one thing you just have to be careful with, notice that when I put this particular piece in there and when I put this particular piece in there, you might think to yourself, why don't I have y dy dx there? Because I wasn't taking the derivative of y, it was just being multiplied times the second term, which was y in that case. When I take the derivative of the y part, which is in the other pieces, that's when you have to tack on the dy dx as a multiplier. Okay, now let's go ahead and solve this thing. So I got to collect all the dy dx terms and then move everything else to the other side. So I've got a dy dx term here, a dy dx term here. Oops, I should have gone a little bit further. So I'm going to keep those over here. So I'm going to clean it up just a little bit, put the dy dx on the end. I'm going to move the x over to here in front, so that'll be 2xy dy dx. I tend to like to write them in alpha order if possible. And then I'm going to subtract the 2xy and the y squared to the other side. All right, now I can factor the dy dx out of the left side, leaving x squared plus 2xy equals -2xy minus y squared, and then divide by everything in the parentheses, and we will have our derivative. -2xy minus y squared over x squared plus 2xy. There's our derivative. Again, dependent upon both x's and y's. And nothing in there is going to simplify any further. I mean, you could factor a negative out of the top, but that's just about it. All right, I think I'm going to stop this video there. We'll come back and do a bunch more examples.